Hi, I'm Leonardo Rosendo.
My name is Ivan Pontes.
I'm Lucas Uzena.
And my name is Gabriel Ramado. And together we are Aperture Open!
We participate in RoboCup Junior in Soccer Open category, representing Colégio Objetivo from São Paulo City, Brazil.
Our team participated in many international RoboCups in lightweight, and we hold the Brazilian first place and the America's third place in Open.
Now we will explain about the hardware of the robot. This is a robot. It has 3 PCBs that are separated by PLA support and connected by 2 flat cables. The boards were designed in EZDA and printed by JLC PCBs. Let's make a quick comparison of the evolution of the robot. Due to the change we made to use a conical mirror in RoboCup Americas, the ultrasonic sensors were removed to save space on the robot. In the final steps of the building process, were discovered that since the compass was lowered, the magnetic interference of the motors made the compass unusable. So for this robot, we used only a gyroscope. We included a kicker and dribbler systems and started to use motors with encoders. We also integrated the components of the top and middle boards in only one board and included a board for the kicker. The top board has 17 cm in diameter and has support for one ST-emitter2 F405, one gyroscope, one Open V87 Plus, one step down of 5 volts, one RoboCup Junior Bluetooth module, one 8C05 Bluetooth module, one LCD screen, 3 LEDs, 3 push buttons, and 2 rocket switches.
The bottom board has 14 cm in diameter
and is composed of 32 reflecting sensors, each one using one LED and one phototransistor, 2 multiplexers, and one step down of 3.3 volts. Kicker board has step of 48 volts, 2 MOSFETs, 4 capacitors, and support for a solenoid used in the kicker. We have seen robots with reflecting sensors in different quantities and shapes, in general arming the reading precision. So we used a circular shape with 32 sensors and a bigger perimeter, making the reading of the data easier and increasing the precision. To use fewer pins for the reflecting sensors, we use 2 multiplexers that only need 4 digital pins to read 16 sensors each. In total, including 2 analog pins to get the readings, only 6 pins are used for the 32 reflecting sensors.
Our robot used the kicker board to increase the voltage from 12 volts to 48 volts and stores it in 4 capacitors. The kick is activated using the 2 MOSFETs. Because of the lack of space on the robot, we used the case of the motor as the dribbler roller. We use parts molded in silicone to provide grip to the roller. And that's it for the hardware part.
Come here, let's talk about the software. The software of the robot is divided in 4 parts: location, communication, movement, and decision. The programming language used on the robot is C++, using Python only for the camera.
The location part is responsible for reading the sensors and interpreting the data collected. It gets the angle of the robot in relation to an offset and in which direction is the robot on a line. We then implement this information on the camera code for a complete positioning algorithm. The camera is programmed in OpenMV and uses a color tracking system to identify the goals and the ball. In the STM part of the code, with the absolute position of the goals on the field and relative angles to the robot, we use trigonometry to find the position of the robot on the field, and we feed the position of the ball. We also calculate the ball speed and use it to predict its trajectory.
For communication, we use a serial protocol based on a list of 4 bytes. Their functions are identify to verify that it's a real message, address to notify the message usage, and the last 2 bytes are the message itself. On the robot, the communication is used with Bluetooth and between microcontrollers.
The movement part controls the robot's motors, either in axial movement or rotating around itself. For axial movement, we use trigonometry to divide the right forces to each motor. For rotating, we use a PID either in a predefined offset or in any direction.
The decision part tells the robot what to do with the data received from sensors based on a predefined strategy. We played against teams from different countries and we noticed the importance of the strategy when the hardware of the robot is under its limits. And the same strategy can be better against better teams, but works surprisingly well against other teams that only considering hardware should be better too. Defensively from the methods of strategy management normally used in the Open, we use a method inspired in SSL soccer teams, the state machine. In the code, there are behaviors like the striker and goalkeeper, in diverse states such as kicking or going to a specific position. To control the states and behaviors, there are transitions activated by either events or conditions. This way, we can make a strategy much more fluid and exchangeable, possible to decide which states will be used, what is the robot's behavior, and how it will play based on analysis made of the team we are playing against.
So, that was the general explanation about our robot. This was only our first season in Open and we already learned a lot. We plan to keep the same robot for the next season, focusing mainly in software and new strategies. We are really excited for this and for the future competitions, and we sincerely thank you for watching this video and supporting us. See ya!